Today's event includes forward-looking statements which are subject to risks and uncertainties. Please refer to our SEC filings available at intc.com for more information on the risk factors that could cause actual results to differ materially. We will not be discussing the proposed Mobileye IPO today. Today's event does not constitute an offer to sell or the solicitation of any offer to buy any Mobileye securities.
Welcome everyone to Mobileye's Under the Hood, our annual session of what's going on with Mobileye, past, present, and future. So I'll first start with 2021 in numbers. We had really a record year, 41 new design wins with more than 30 OEMs. This is really a record figure. Those new design wins are responsible for a pipeline of 50 million cars going forward. This is compared to 37 million in 2020. Our revenue rose year on year by about 40%. So we finished 2021 with $1.4 billion. And during 2021, there were 188 vehicle models launched with Mobileye inside. On the right-hand side, you can see how the number of EyeQ chips that have been shipped. In 2020, it was 19.3 million units, and 2021, 28.1. And overall, since 2007 till today, we celebrated 100 million EyeQ chips shipped to date. This means 100 million cars on the road with Mobileye's technology. During 2021, there were also some industry first launches. We launched the first level 3 vehicle with Honda in Japan. We are responsible for the computer vision. A 120 degrees field of view with an 8 megapixel camera, very, very high resolution camera. This was launched this year with BMW. We're talking about cloud-enhanced driving assist using our crowdsourced technology called REM. This has been launched with Volkswagen this year. And yesterday at the press conference, I had a chat with Dr. Herbert Diess, the Volkswagen Group CEO. And we kind of showed under the hood of what this car can do with the cloud-based assistance. And really the crown jewel still with the level 2 is our 11, it's called Supervision, 11 cameras around the car, powered by 2 EyeQ chips with an ECU designed by Mobileye. Already a few thousands of cars have been shipped in China, and through over-the-air update throughout 2022, ADAS features up to navigate on pilot, hands-free navigate on pilot features would be OTA'd onto this platform. Just in terms of a few more figures, if you look at our infrastructure data, we have 200 of petabyte data, partly on-prem, partly cloud on AWS. Just to give us a reference to the scale of this figure, Intel has 238 petabyte, all of Intel. 16 million clips covering 25 years of driving. In terms of compute, 500,000 peak CPU cores. These are all based on spot instances. Just to give you kind of a reference figure, this is 10 times more than Skyscanner. We have 50 million monthly runs. That means 100 petabytes being processed every month on 500,000 hours of driving. This is really very, very powerful. So the way we built this presentation is today we're in 2021. Let's look kind of 4 years backwards, 2017, and then 4 years forward to 2025. So back in 2017, we kind of laid down kind of 3 fundamentals of our strategy. One was what we called REM mapping, which is crowdsourced technology based on a driving assist system. So every car with an EyeQ chip has the capability to send pertinent data, very sparse data to the cloud, And in the cloud, we developed in the past 5 years algorithms to piece all this data together and create high-definition maps to power both premium driving assist and also autonomous driving. We lay down another pillar, which we call the true redundancy, in which when we build an autonomous car, it's based on a number of different types of sensors, cameras, radars, and LiDARs. But we built it in a way which is the cameras and the radars or LiDARs are separated in two subsystems that don't talk to each other. So we build an end-to-end driving experience, perception, driving policy, control using only cameras, and an end-to-end driving experience or the sensing state, the perception, end-to-end using only radar and LiDARs. And this creates an element of robustness. When you put them together, you get a redundancy. And the third pillar is about our safety model, which we call the RSS, Responsibility Sensitive Safety. It tackles the problem of how do you define what safe driving is? What is the borderline between reckless driving and careful driving? How do you merge into traffic in a way that allows human level driving, but is and also safe and useful? We published that in 2017, and throughout the years, it's kind of a very fundamental building block in worldwide standardization. So those were kind of the three pillars, and those three pillars are kind of powering two divisions of Mobileye. One is premium ADAS, what we call a level 2 plus. We are referring to a system which has multiple cameras. At the extreme, it's full 360 degrees cameras, a full operational design domain, so full capability, very low cost because it's powered only by cameras. And REM is built in. That means the cloud enhancements to pilot functions provide geographic scalability. And then the RSS-based driving policy, which I'll say a few words later in the presentation, allows for very lean compute in terms of planning. Then there is level 3, level 4, which is from conditional autonomy to full self-driving. Here comes the second layer, second subsystem for redundancy of radars and LiDARs. REM enables scale, RSS enables the safety guarantees, and radars and LiDARs, they depend on the desired ODD. So full level 4, we have a 360-degree coverage of radars and LiDARs, and for level 3, depending on the ODD. So where we are today. So that was, we established that 4 years ago as a target where we are today. So in terms of REM mapping, we built kind of the largest crowdsourced fleet for mapping. We receive today 25 million kilometers every day. During 2021, we collected 4 billion kilometers of data. 2022, if you start with 25 million kilometers per day, it's roughly 9 billion kilometers in 2022. We have a fully functional level 2 plus, which is kind of drive everywhere. We have AV test vehicles deployed in many cities, in New York City, Detroit, Tokyo, Paris, Munich, of course, and Israel. True redundancy. Supervision is the productization of our camera subsystem, has been launched with Zeekr, a Geely brand in China. So a few thousands of vehicles have already been shipped to customers, and functions will be OTA'd over-the-air update throughout 2022. We have a radar LiDAR subsystem complete, means it's providing an end-to-end driving experience without cameras. And we unveiled our robotaxi, which unifies both subsystems, cameras and radars, LiDARs. We unveiled that at the IAA back in September. And from middle 2022, it's going to be on the road and then fully homologated by the end of 2022, at which time we'll be able legally to remove the driver from the car. And finally, the RSS safety model, we published it in 2017. There were about 2 papers around that. And it's really a cornerstone of many standardization efforts worldwide. The example is the IEEE 2846. It's a working group. It is chaired by Intel Mobileye. There are more than 30 leading industry players in that group. It will be published in few months. And through RSS, we also have a very, very lean driving policy, and that enables level 2 at scale and also a level 4 at scale. So let's look at our kind of testing footprint. So we showed, throughout the year, we kind of uploaded unedited drives in Israel, in New York City, in Munich, Detroit. And I'll show you 2 new sites, Paris and Tokyo. The Paris site is a collaboration with the RATP. RATP Group is the biggest public transport operator in France. And this is with collaboration with Moovit. Moovit provides the layers above the self-driving system for ride-hailing. Employees of Galeries Lafayette can use the car to drive autonomously from work to home. There's a safety driver at this point in time. And let's run this clip. It's fast-forwarded, but you can see kind of the richness and the challenge of driving in Paris, and the kind of challenges our car needs to face while driving in Paris. Here is Tokyo. We have a site in Tokyo where many OEMs have already experienced our driving technology, autonomous driving technology. Tokyo, it's left-hand driving, lots of pedestrians, narrow roads. It's also a driving experience that is somewhat different from other locations in the world. And using our crowdsourced data by building those HD maps allows us very, very efficiently to expand our testing. So where we are today in terms of cloud-enhanced level 2. So our REM technology was designed to power autonomous cars, but also it can be very, very powerful addition for enhancing driving assist. So Volkswagen Travel Assist 2.5, the first vehicle is the electric vehicle ID.4. It's powered by REM maps. Yesterday with Dr. Herbert Diess, the group Volkswagen Group's CEO, we had a chat and a drive with the vehicle to see how it works. So you can drive in areas where you don't see any lane marks, yet the availability of lane keeping assist and lane centering is maintained because of the map data. With Ford, we just announced the next generation Blue Cruise is going to be powered by REM maps. Of course, the Zeekr Supervision is productizing our computer vision subsystem for hands-free level 2+. It's also using REM maps. In terms of level 3, we launched with Honda and Valeo in Japan. We are responsible for the computer vision. BMW 7 Series is coming out this year with a level 3 system in collaboration with Mobileye and Aptiv. And we have future programs with higher ODD for level 3 that we'll announce down the road. In terms of level 4, we unveiled our robotaxi at the IAA back in September. It has the integration of our camera subsystem and radar LiDAR subsystem. It will be on the road from middle 2022 and homologated by the end of the year, at which time we will be able to remove the driver in Germany and in Israel. We have signed many robotaxi, AV, shuttle, goods delivery deals with the SIX, the RATP Group, the Transdev, Uldelv, Willers, more recently with the Murabeni in Japan for goods delivery. And we also received, we announced this week, we received the first design win for consumer level 4. That means a car that you can buy, not a ride-hailing technology, a car that you can buy with the Geely, the Zeekr brand. SOP is going to be early 2024. So this is the design win with the Zeekr. It's going to be powered by 6 EyeQ5 chips and SOP early 2024. So where does all of this lead us to? It leads us to kind of 3 business pillars. One, there is a new category emerging in driving assist. It's kind of a premium ADAS. We call it level 2 plus. It's based on the extreme side. It's based on full surround sensing. Like in the Zeekr, we have 11 cameras, 7 long-range cameras, 8 megapixels, and 4 parking cameras. There's cloud-based enhancements using our REM maps. There's a firmware over-the-air update involved, both for updating functionalities, and also streaming the map data to the car, providing a cloud-based enhancement. And there's a full sense, plan, act cycle on a very, very wide operational design domain. So basically, the ODD is the 2 clips that I've shown you right now with Paris and Tokyo. This is the kind of ODD that the car is able to support. This is level 2. There should be eyes on and minds on by the driver. The second emerging pillar is, as we all know about it, this is the level 4 robotaxi. It's geofenced. The cost of the system could be in the tens of thousands of dollars. And this is our robotaxi platform that we unveiled back in September at the IAA. And then a new category that's emerging in the 2024, 2025 timeframe. This is level 4 consumer AV. What it has that the robotaxi does not have, one is that it should drive everywhere. And this is where our mapping technology, the REM mapping technology, becomes very, very critical. So it's not just geofenced capabilities. And the cost, we believe that they cost an MSRP to the customer around $10,000 means that a bill of materials cost should be way below $5,000 to support a consumer AV. And Mobileye is working on all three categories. So to continue where this leads us, when we look at autonomous driving, the future can move in 2 directions. Both of them, one of them, one is the robotaxi, moving people, moving goods. Mobileye is active there, and many companies are active, like Waymo, Argo, Cruise, Aurora, etc. Then there's another possibility, which is a consumer AV. You purchase a car, the car is enabled, has a level 4 capability. You press a button, and you can have your eyes off and minds off the driving experience. Mobileye is active there. Tesla, of course, this is kind of the flag, the torch that leads them forward. Perhaps Apple, as far as anyone knows what Apple is doing. But one needs to note that these 2 futures are not equivalent. That means the consumer AV future contains inside it also the robotaxi. Because if you can purchase a car, then of course you can add to it the layers of ride hailing and sell it to PTOs, to public transport operators, transportation network companies, and provide a service. The other way is not clear. That means if you have a robotaxi technology which is geofenced and expensive, this does not lead to a consumer AV. For a consumer AV, you need geographic scalability, and you need to self-driving system cost way below $5,000. And we argue that a consumer AV, this needs to be purpose-built. You cannot start with a robotaxi technology in terms of scalability, lack of scalability, and high cost, and bring it to a consumer AV. It really needs to be purpose-built. And this is really what Mobileye is doing. We're active on both fronts, but thinking about scale, thinking about cost and scale, and designing everything around cost and scale. Now, doing both is not just about hedging how the future is going to unfold, because there are very strong synergies between the robotaxi and the consumer AV. There's lots of learnings to do by deploying robotaxis that will be very, very critical for the next stage of consumer AV, because robotaxis can come earlier than consumer AV. The 2022, 2023 timeframe looks like a very, very reasonable timeframe for robotaxis, and 2025 looks like a reasonable timeframe for consumer AV. So let's look at what are the criteria for a good solution that can cover both futures. So we divided them into kind of three pillars. One is capabilities. You would like to support a very wide self-driving operational design domain. Whether it's highway, rural, urban, arterial roads, to provide a very, very wide ODD, and human-like driving policy. It needs to merge into traffic in a very smooth manner, similar to the way a capable human driver would merge into traffic. The next pillar is robustness. It should have a very, very high mean time between failure, much, much higher than the average human driver. Somewhere 10 times higher, 100 times higher, 1,000 times higher, but it should be higher. And third is efficiency. Efficiency is cost. As I said, we want the compute and sensors to be way below $5,000, and also support scale, being able to drive everywhere. So those are the three pillars. What is Mobileye's approach in supporting those three pillars? In terms of capability, we support full operational design domain, full ODD, from level 2 to level 4. That means we claim that the differentiating factor between a level 2 to level 4 is not the ODD, it is the MTBF. What is the mean time between failure? If the mean time between failure is lower than the average human driver statistics, then it's a level 2 system. If it is higher, then it can be a level 4 system. So we support a full ODD in terms of perception, driving policy, and control, even for a level 2 system. In terms of robustness, we have two principles. One is the RSS, responsibility sensitive safety, the model that we formal model that we published back in 2017, and today is the cornerstone of many worldwide standardization efforts for standardizing the regulation for level 4. And our concept of true redundancy, in which we take cameras, radars, and LiDARs, but we don't treat them alike. We divide them into two separate subsystems. One is the computer vision subsystem, means perception being done only by cameras, no reliance on radars, no reliance on LiDARs. And then another subsystem where the perception is done only by radars and LiDARs without any input from cameras. And then we integrate them and create a redundant system, redundancy by two separate subsystems. This increases the robustness, increases the mean time between failure, and allows also easier validation of the system. In terms of efficiency, we have here four elements. One is purpose-built system on chip. I'll spend some time on it. The next generation of radars, we call the software-defined imaging radars, and I'll explain why I'm making such a big fuss about radars. Lean compute. It's not only the SoC should be purpose-built, but the compute supporting a level 4 should be lean, and I'll explain what I mean by lean. And then the REM crowdsourced mapping is a critical element to allow for scalability, and this is the fourth element. So in the remaining of the talk, I'm going to focus on those four elements, one by one. First, purpose-built SoC, software-defined imaging radar, lean compute, and the REM crowdsourced mapping. Where we are, what is the status on each of the four elements? Because really, those four elements are critical in building a good solution. So our SoC. Our SoCs are called EyeQ chips. Today, we are the fifth generation. We have millions of, in terms of design wins, supporting many, many millions of EyeQ5 chips going forward. The BMW that I mentioned, the 120 degrees 8 megapixel is supported by EyeQ5. Audi launched a system with EyeQ5, and there are many more. What we are announcing today is 3 new generations of EyeQ. The lowest is the EyeQ6 Lite. This is supporting level 1, level 2 ADAS. Very, very low power consumption, around 3 watts. So it's behind the windscreen. It's a single box driving assist, very, very powerful. Then an EyeQ6 High, which is roughly equivalent to between 2 to 3 times EyeQ5. This is going to power the next generation of our supervision. And EyeQ Ultra, which takes all the learnings that we have done throughout the years of building an AV technology and understanding what exactly are the workloads, what kind of silicon architecture to support those workloads. After all these learnings, we are ready to design the ultimate chip, which is basically an AV on chip. We call that EyeQ Ultra. So this will support a single chip, monolithic chip, to support a full self-driving. Inside the chip, there are internal redundancy with an external MCU, ASIL-D MCU. This entire system will support an ASIL-D system. So let me start with the crown jewel, with EyeQ Ultra. So Mobileye over the years, have developed our accelerators. Come in 4 different families. One of them is just pure deep learning calculation. Another one is somewhat similar to an FPGA. It's called the CGRA. Another one is SIMD, a very long instruction word that's similar to a DSP. Another one is a multi-threaded barrel CPU. Each of those cores is responsible for a different type of workload. EyeQ Ultra has 64 of these cores. So 64 accelerator cores. It's running on 5 nanometer process. It will have 12 RISC-V CPUs, 24 threads each. It will have also a GPU and ISP for visualization purposes. And it will support 176 deep learning int 8-bit deep learning operations. So 176 sounds like a small number compared to what we hear from our competitors. It's roughly 1/10 of what we hear from our competitors, 1/5 to 1/10, because it's not only about TOPS. It's really the efficiency is born out of really understanding this very, very tight interplay between hardware and software, what type of cores, what type of algorithms to support those cores. And if you take for example, the supervision, what's now on Zeekr and what I've shown you in the 2 clips with the Paris and Tokyo, it's running on 2 EyeQ5 chips. So it's supporting processing of 11 cameras, 8 megapixels, so very, very high resolution, and the full driving policy, the full sense, plan, act cycle on 2 chips, which each of them is 15 tera operations per second. So it's very, 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 very light in terms of computing power. So this shows that you can be very efficient and be lean in your compute if you design this properly by designing both the hardware and the software together. So 176 TOPS, this is roughly 10 EyeQ5 chips. And this is based on all these learnings that we have been doing. 2 EyeQ5s are powering the supervision today, which is the computer vision subsystem of our AV development. We have 6 EyeQ5s. This is going to be for the limited ODD level 4 2024 Zeekr. We have 8 EyeQ5, which is powering our robotaxi. So all these are learnings that make us to believe that 10 EyeQ5s is all what we need as a single chip to power a robotaxi. So with such a chip, the entire ECU, the entire electronics of supporting a full level 4 system will be way below $1,000. And this is really game-changing in terms of cost. And power consumption is very, very light. The entire system will be below 100 watts. EyeQ6 High, so EyeQ6 in terms of TOPS is about 3 times EyeQ5. with just 25% more power consumption. It has 14 of our cores compared to 64 cores of the EyeQ Ultra. It's 7 nanometers, just like EyeQ 5. Supports 34 tops. It has GPU ISP to support visualization. And our next generation of supervision, which today runs on 2 EyeQ 5s, will run on two EyeQ 6. And there are many configurations that one EyeQ 6 high will be sufficient for. So this is, it's being sampled this year, the first engineering sample end of this year, and volume production in 2024. I forgot to mention that EyeQ Ultra will be engineering sample would be end of 2023, so less than 2 years from now, with volume production in 2025. Then comes EyeQ 6 Lite, 7 nanometer, supports 5 tops. It is our EyeQ, the power horse EyeQ today, powering ADAS, is EyeQ 4 mid, so it would be about 5 times stronger than EyeQ 4 mid in terms of computing power. Very low power consumption, about 3 watts. We have already committed deals for design wins over 9 million units for EyeQ 6 Lite. Has been sampled half a year ago, and it would be for volume production of 2023. So these are systems that are designed for behind the windscreen, very powerful compute for a wide range of driving assist features. So that was the purpose-built system on chip. Next come software-defined imaging radar. This is something that I talked about last year. This year I'm going to kind of update the status, but more importantly, show what this radar can do. So why are we interested in radars? So when we look at today we're talking about 2 subsystems. One is camera-based subsystem, this is our supervision, and another subsystem is 360-degree LiDARs, time-of-flight LiDARs, providing 360 coverage, and a number of radars to complement it. That's a subsystem, and that subsystem performs independent perception, and the computer vision subsystem independent perception. Going forward, we want to both create more robustness and reduce cost. Now, one rule of thumb is that the cost of a radar is somewhere between 1/5 to 1/10 of the cost of a LiDAR, and I'm talking asymptotically. LiDAR costs will go down, radar costs go down. It's about 1/5 to 1/10. The problem is that radars today, they are useless as a standalone sensor. Now, you cannot create a sensing state in congested traffic, separate pedestrians and vehicles that are very close to each other with the kind of resolution and the kind of spec that radars have today. But radars, the evolution of radars is very, very promising. And we set out the goal about 2 years ago to build a high-definition radar, a high-resolution radar. We call this software-defined radar, because everything is configurable through software, even over-the-air update, configuring the transmission, the transmitters, configuring the receivers, the signal processing. Everything is configurable through software, and build it such that with the right algorithms, with the right deep learning algorithms, we can create standalone sensors. It can do what a LiDAR can do. So if we achieve that, then the sensing configuration in the 2025 timeframe would be that you have only a single front-facing LiDAR. You have front-facing, you have 3-way redundancy: LiDAR, cameras, and this imaging radar. And then surround, you have the cameras provide full surround, and the imaging radar is a full surround. You don't need LiDARs as a full surround, because the radars will be a standalone system. Just like today, the radars and LiDARs are a standalone system. So this would be game-changing in terms of cost, and even add more robustness, because front-facing now will have 3-way redundancy and not 2-way redundancy. So back last year, I described the spec. I'm not going to spend too much time on the spec. The spec hasn't changed. It's about above 2,000 virtual channels. It's 48 by 48 transmitters and receivers. Very high resolution. Dynamic range is 100 dB. Dynamic range is really unheard of. And the spec elements are very, very powerful. We completed sampling all the chips of the system. We have the radar also built. You can see here the picture of the radar. What I want to focus now is to show you some examples of what this radar can do together with the right algorithms supporting the radar. So I'll do it step by step. Before I run this clip, on the left-hand side, you see radar points. Green versus yellow. Green is kind of elevation. So green is on the floor, yellow is going up. The red and blue dots are, the blue is vehicles that are away from us, and red are vehicles that are coming, vehicles or other objects that are coming towards us. So first thing that you can see before I run the clip, you can see that the curbs, the right and left curbs of the road, you see those green dots that show you that the radar sees the curb. But now let's run this. And you can see the complexity of the scene in terms of how many cars very close to each other, pedestrians, very congested scenario, and we'll stop in a point where you have cones, and you can see here that those cones are marked in yellow on the left-hand side. You can see them clear. So our deep learning algorithms have not yet been trained on detecting cones, but the data exists in the radar output. Let's go for another example. So here we're going to go under a bridge. By the way, the deep learning algorithms are trained to detect vehicles up to 50 meters. The data supports much more than 50 meters. What you saw before was you saw the cars on the right, even hidden by the guardrails. You saw the car inside the tunnel was not distracted by the tunnel. So all sorts of radar perception that with existing radars is quite difficult to do. You can see here that the curb, the left and right curb, you see them very, very clearly in the radar output on the left hand side. Next, you are going to see on the left hand side a motorcycle, and then we are going to follow that motorcycle. So here's a motorcycle. You can see the blue dot on the left hand side, and now we'll continue to run. Even if the motorcycle is off bore site, which is very challenging for radars, it's still detected, and you can see that on the left-hand side, that blue dot going forward in very congested traffic. So to give you an idea of the quality of data that is there, because reading radar output is difficult. It's not like reading image output or reading LiDAR output. So we trained two networks. This is not actionable. This is just to show what this radar can do. We trained a network that was trained on radar input, LiDAR output. So we put a radar and a LiDAR together, and then we used the LiDAR as output for a neural network to map the radar to LiDAR. So what you see here is on the left-hand side, the scene seen from a true LiDAR. On the right-hand side, the mapping from our radar, this neural network maps the radar output to a LiDAR representation. And as you can see that they're almost equivalent. Let's look a bit more. Let's start looking at the left-hand side. So on the left-hand side, I'll run this. Left is true LiDAR. Right is the mapped radar to LiDAR representation. It looks almost identical. So the point I want to make here is not the beauty of this neural network that we designed. There's nothing special about that neural network. The point I want to make here is the quality of the radar data. if you can take that radar data and generate a representation that's almost equivalent to a LiDAR representation, it means that there is gold to extract from this LiDAR. Let me show you on the right-hand side. Same thing. On the left, it's true LiDAR. On the right, it's the radar mapped through the neural network to a LiDAR representation. And you can see they're almost equivalent. Okay? We did another experiment. This experiment, let's just say, let's train a neural network to map the radar output to an image, to a camera image. So again, we took the radar and the camera together, and then we used neural network to train it. And what you see here, so this is not a true image. It looks like a true image. There's all sorts of deformations here, but it looks like a true image, but it's not. It's neural network mapping the radar output to an image. You can see even the guardrails, you can see the vehicles. So this is just a way to kind of give you the idea of the quality of this radar output. So the purpose of all of this is to take such a radar, which again, the cost is 1/5 to 1/10 of the cost of a LiDAR, and use it as a standalone sensor in the 2024-2025 timeframe. And then we can reduce cost considerably and be left only with a front-facing LiDAR to create a three-way redundancy. Okay? Talking about LiDARs, as I mentioned last year, we have another division building a frequency modulation coherent wave LiDAR, which is it's a 4D cloud of points because there's also velocity. It's like a Doppler effect. And we already finished we sampled what we call LiPro. It's the chip that it's multi-channel. It processes, it's a system on chip that processes all the data coming from our silicon photonics. Silicon photonics supports 90 vertical challenge, and there's channels, and there's also a foveation to create a more vertical range. So it's basically 1D scanning. You have 90 lines, 1D scanning, and some vertical foveation. And again, all of this would be volume produced in 2024. So what we have covered so far, first is AV on chip. It's a monolithic chip. In a 2024, it will be on the road. 2025 in mass in volume production. Software-defined imaging radar that can take the play, that can be a standalone sensor in terms of redundancy. So you can create a layer of cameras, a layer of radars, and you have two subsystems. And then take a three-way redundancy forward-facing with the LiDAR as well. So that with the monolithic AV on chip, we get a system which is way below $5,000. Right? So next on lean compute, next on efficiency is lean compute. And here I want to talk about the cycle of sense, plan, act. So sense is the perception. We all understand what perception is. You want to understand the road around the car 360 degrees, about where the road users are, their kinematics, stationary objects, obstacles, traffic lights, curbs, lane marks, and so forth and so forth. This is sensing. Then there is planning. The car needs to make a decision. It's all about decision making. What would happen? This is kind of what would happen if I do something. That's the type of reasoning. And the idea is that you want to change lane. How do you change lane in a way that is not reckless? How do you decide when to change lane, how to change lane, signal through your motion to other road users, do it in a way that is not reckless, yet is useful. That means you can merge into traffic. So this is all about planning. And then act is the control of the vehicle. So now, this planning, which is called driving policy, it's coming from robotics. This is, the amount of compute that is invested there could be very, very high. And I want to explain why it could be very, very high and why Mobileye has a very, very lean approach to it. So first, let's kind of define what is driving policy. And all what I'm saying now is kind of a very, very, it's a teaser to a much more detailed talk that is given by our CTO, Professor Shai Shalev Schwartz. So I'm going to spend 5 minutes on it, and then link you to Shai's talk with all the details. So first, driving policy. The definition of driving policy is the mapping between the sensing state, what all other road users are doing, their kinematics and obstacles and lane marks and so forth. Everything around the car is called a sensing state. And you have kind of an engine that maps it into action, which is longitude and lateral control of the vehicle. So why it's considered a hard problem? First, there's no ground truth, unlike with sensing, where you have a ground truth, where are the vehicles, where are the pedestrians, traffic lights, and so forth. Actions may have a long-term effect. A very simple action that you do now may cause an accident a few seconds later or a few minutes later. So you really have to roll out the future, kind of extended rollout of the future in order to decide on the correct action. Then there's this closed loop notion where actions affect other road users. Right? You're not the sole agent in this game. Your actions affect actions of other road users, especially when you're changing lane in congested traffic. And you must handle uncertainties about the futures. What other road users are going to do. So there are many techniques around this, and try to picture it in a kind of a non-technical way. So there are 3 dimensions here. So one is the amount of compute. So let's look at the left-hand chart. One is the amount of compute. That's the vertical axis, and then say the quality of the solution, the quality of the search, in terms of what best action to do. So brute force is very, very simple to define. You're kind of rolling out the future by looking at all possible actions for all possible agents for step 1, and then again all possible actions for all possible agents. So it's kind of a tree that is growing exponentially large. That's the brute force approach. So clearly the amount of compute is unwieldy, but you'll get a very, very good solution at the end. The problem here is compute. The technique that is really mostly used in robotics and also in autonomous driving development is the MCTS, Monte Carlo tree search. And the idea is to take this tree and prune it. So the first thing that you assume that you know what is the driving policy of other agents. Now, given a state and an action, what would be the next state and so forth. And then you start pruning this tree with all sorts of heuristics, neural networks that kind of learn how to prune that tree. And the quality of search will depend on the amount of computing budget that you have. If you have a small computing budget, and the quality of search would be low. If you have a large computing budget, the quality of search would be high. Then there is the MDP, the Markov decision process, in which the quality of search would be very, very high, but you are making a very strong assumption about prediction of what other road users would do. That means you're kind of statically assuming where another road users would be, not only in the next second, but in the next 10 seconds, in the next 100 seconds, without taking into account the interaction with other road users. If you agree with this assumption, then MDP is very, very efficient. So then comes this, the line on the right-hand side is what is the realism of assumptions. So the MDP is the least realistic, because you're assuming that you can predict what other road users will do in a kind of looking forward in time in a lengthy way, and not using a closed loop assumption. That means their trajectory is independent of other road users' trajectories. The Monte Carlo tree search assumes that you know what is the policy, the mapping between state and action of other road users. It may not meet reality. And brute force has the least number of assumptions. So you can see here that in order to get a good solution, right, MDP is not realistic. And MCTS, you'll really need to spend a big computing budget in order to get to a good quality of search. So this is why driving policy historically require a lot of compute. So here comes what we what we did back in 2017 in terms of building a safety model. So the paper that we wrote was quite lengthy. It contained also inside the driving policy, but in all our public appearances, we never, emphasized the driving policy. We emphasized the regulatory framework of what RSS enabled. So RSS is saying the following thing. First, let's define what are reasonable boundaries on the behavior of other road users. Because when we humans, we drive, we make assumptions. Let's try to capture those assumptions and capture them in a mathematical, in a formal manner with parameters. Then we can communicate with industry actors, with regulatory bodies on setting the parameters of those assumptions. So once you set up those assumptions, then the theory says, let's take the worst case. Let's not predict what other road users will do. Let's take the worst case under those assumptions. And then we have there a kind of a formal theory, which is based on induction, that shows that under this kind of framework of you agree on assumptions and you take the worst case, you can prove that you'll never cause an accident. Okay? So this provides formal guarantees. What I want to spend time, and here is just to show that it was a really successful framework in working with regulatory bodies. For example, the IEEE 2846 is chaired by Intel Mobileye, consists of 30 leading industry players, and an RSS is really the starting point of asking those kinds of questions. The EU Commission, the UK Commission, ISO, and so forth. But what I want to emphasize here is not the regulatory framework, is how does this affect driving policy? So far RSS what was presented as a regulatory framework, which is that was the purpose of the development of RSS, but we use it also as a foundation for our driving policy. Basically what it says is that if we use induction and analytic calculations, that means you need to present the problem in a way that will support analytic calculations. RSS, the formal guarantees of RSS is that it couples all plausible futures, not all futures, all plausible futures, because we made assumptions on how road users drive. So couple all plausible futures into the present. So it's not dynamic programming like MDP, this induction principle, but same effect of coupling all plausible futures into the present. And this yields efficient, it's realistic, it's the quality of search is maximal, and you have also explainability. Where does the neural networks come into? They come not at the safety layer, but at the comfort layer. Instead of predicting what other road users would do, we detect intentions. Those intentions could be, give way or take way. Intention could be that this car is now going to do a parking maneuver, is going to do a U-turn. That we have a long list of intentions, and we use neural networks in order to detect those intentions, and they control the parameters of RSS. So altogether, if now we place our RSS-based driving policy in this chart, we have the efficiency of MDP, but without the lack of realism in terms of assumptions of MDP. So this creates a very, very lean policy. And going back to kind of our computer vision subsystem, to supervision, all the clips that we have showing, there is a full ODD driving policy. The car is driving in very, 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 very challenging situations, doing full perception, 8 megapixel cameras, 11 cameras, the full sense, plan, act cycle, and only 2 EyeQ5 chips. So it's a proof that our driving policy is very, 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 very lean. And this was just a teaser. There's about a 1-hour talk by Professor Shai-Shalev Schwartz, our CEO. Just search Mobileye's lean driving policy, and you'll find that the YouTube clip. So just last in terms of efficiency is our REM crowdsourced mapping. Travel Assist 2.5 by Volkswagen is using, we announced that yesterday. We had at the Intel press conference a session with Dr. Herbert Diess, the Volkswagen Group chairman. ID4 is powered by the REM maps. Here's an example of the drive that we did together. Now that we took a right turn, you can see that the magenta lines are the drivable paths coming from the map, and you don't see any lane marks. So a system without enhancement of this cloud-based enhancement of the maps would not be able to activate lane keeping or lane centering, because it wouldn't know that there are two drivable paths here and exactly where they are. Information about the traffic lights, the relevancy, the association between traffic lights and lane marks and drivable paths is also inside those maps. It can power very critical safety functions like making sure that the car will not run a red light. Driving assist will be able to do that if it's powered by such a map. Our coverage is very wide. This is Europe. We have 2.5 kilometers of road already covered. We harvested 4 billion of kilometers in 2021. We are now at a rate of 25 million kilometers harvested daily. So it's growing every year. It's growing. In terms of richness of the map, I talked about this last year. There's lots of, it's accurate, geometrically accurate, very rich semantically about drivable paths, road edge, the traffic lights, association with traffic lights and drivable path, crosswalks and the relevancy, stopping point, yield points, common speed per lane, very rich. And we added more richness in 2021. On the left-hand side, construction areas. So every road where there is a construction is colored here in red. On the right-hand side, turn indications. So, for example, in this enlarged block, 12 out of 15 cars turned their right turn signal. So knowing when to turn a turn signal sounds simple, but it's actually very tricky. Getting this information from a crowd enables a much smoother AV experience. Speed bumps is now also included, and also legal speed. Legal speed, knowing what is the legal speed at every section of the road is also very tricky, because you need to associate traffic signs to the right drivable path. It's quite tricky. Getting this from the crowd is something that is very helpful. This also we added. So not only common speed, what's the average speed in a lane, but also what's the legal speed in every lane has been added. Public transportation lanes like bus lanes, toll areas. It's in the center of this figure, and also road types. This is also very useful to enable smooth driving, controlling the parameters of our safety model, knowing what type of road we are driving in. This is also now part of the REM maps. So to summarize, kind of the building blocks that we have been building is first, redefining the evolution of ADAS, this premium ADAS. Where can ADAS asymptotically grow into? And this is our supervision. REM is a very critical element into it, the REM mapping. The lean compute of driving policy is a critical element of it. So this is kind of the North Star of where ADAS can evolve into. Second is the right engineering design to achieve the right mean time between failure using our true redundancy. And from there, we can go to mobility as a service. And the AV on chip, or the EyeQ Ultra, and the software-defined imaging radar are basically two game-changing elements that would enable a future of consumer level 4 in which we have cost becomes a major driver and also geographic scalability coming from REM. So thank you for your patience, for listening to this one hour talk, and see you next year. Thank you.